Hi everyone. In today's lecture, we will again discuss a little bit more about transfer functions and frequency response of first order systems. Okay. And also I'll speak about the realizability. What are practically realizable systems using passive first order RC circuits. So the general transfer function h of s of a first order system can be written like this. Okay. Now this term h of 0 is called as the DC gain. That's your gain of the system when s equals 0. I am using the word gain. It's nothing but the value of the transfer function at s equal to 0, which also translates to omega equal to 0. This is also nothing but h of omega, the frequency response evaluated at omega equal to 0. It's called the DC gain, or the DC gain. Now, if you look at this transfer function, which is h of 0 into 1 plus s by omega z by 1 plus s by omega p, if you look at this transfer function, now I am going to consider this is a very general description of a first order transfer function. Now, the values of omega z can be 0, it can be a finite value omega z, okay, or infinity. Okay, these are the three possible values. And similarly for omega p, it can be 0, you can have a finite value which is any value between 0 to infinity, or infinity. Okay, these are the three possible values. Now if I use that here for in numerator and denominator, they are independently chosen. Based on that, I'll have totally 9 possibilities. Right, I'll totally have 9 possibilities of transfer functions that I can get here. So it's 3 and 3. So you will totally have 9 possible transfer functions for first order systems. Now out of those 9, when omega z is 0 and omega p both 0 0 condition is invalid, because 0 by 0 again it's no longer a transfer function, it will be a constant. So that's not a first order system. Again, infinity by infinity. Okay, infinity by infinity, I am going to eliminate 0 0 as one possibility where omega z is 0 and omega p is 0. Okay, and infinity comma infinity, even that I am eliminating, which means there is no pole, no 0 in the system. Okay, and when it is 0 comma 0, it means there is a pole at DC and there is also a 0 at DC. So both the pole and DC cancel out. So essentially there is nothing. I mean, it's again a constant system. Okay, so if you eliminate that, totally you will have 7 possibilities of transfer. You will actually have 7 possible first order system transfer functions. Okay, here I'll probably write it and I'll show you that only out of the 7, only 6 actually, or rather 5 make sense. So why is that? I'll talk about that. Okay, so we'll just list out the 7 possible transfer functions. So first I'll take with the case of omega z is infinity in this transfer function. So it will be h of 0 by 1 plus s by omega p, which is a simple first order system. Okay, the traditional first order system. Now in the second case, I'll assume omega z as 0. Okay, you have a 0 at 0. So in that case, this transfer function, here I'm using the word omega z. I should have used the word, instead of omega z, I should have used the word sz. Okay, sz and sp. Okay, so now you have a 0 at 0. So the transfer function will be something like this, and a pole. Okay, this is also a first order system. Okay, so here if I equate the numerator to 0, I get s equal to 0. The third case will be when we have finite pole and a finite 0. So the third transfer function is you have both a 0 and a pole. See, everywhere I am multiplying by h of 0, that is to ensure the DC gain. Okay. Now the fourth possible transfer function is when you have 0 at DC, or rather let me just consider the other possibility. You have a finite 0, s by omega z, okay, but your pole is at DC, SP is at DC. You have a low frequency pole or a pole at DC, so that will be s by omega p. Okay, I am again multiplying it by h of z, I will come to that. The other possible transfer function is you can have a pole at infinity, so that will reduce to 1 plus s by omega z into h of 0. And then the sixth case is when you have the sixth case is a trivial case when you have a 0 at 0 and a pole at infinity, so that will be 0 at 0 s by omega z into h of 0. And then the seventh case will be omega z at infinity and omega p is at 0. So in that case, you have a 0 at 0, that's an integrator, omega p by s. So if you look at it, these are the 7 possible transfer functions that you can get from this function, what I have shown here. This is actually, there is a h of 0 multiplied. Now out of this, I will eliminate this and this, because these two are actually, there is no, these two cannot be called as first order systems because they don't have any pole, okay. So these two are eliminated. Now the only other, the other possibilities, we will now consider the other possibilities and see which are realizable and which are not realizable, okay. Now this is a perfect integrator. So if I feed voltage as an input and take voltage as an output, then we can't realize this using purely passive circuits, okay. There is a reason for that. We will discuss that very slowly. I'll slowly discuss that. And similarly, this transfer function here, it has a pole at DC and a finite 0, and we will show that even this transfer function is not realizable, okay. This transfer function is also not realizable. And in this one, this transfer function is easily realizable, but there are certain conditions under which that can be realizable, okay. So eventually we will only be discussing, we will mostly be encountering 3 kinds of transfer function, the 1, 2 and 3, okay. These are the 3 transfer functions which we will encounter when we are giving voltage as an input and taking voltage as an output, okay, or current as an input and current as an output, using simple first order RC circuits, okay. And even the third transfer function, it's valid only under certain conditions. Now first, I'll lay down another simple criterion, that h of 0, okay, the DC gain of the system has to be always less than or equal to 1 for passive circuits. So again, we will see how does that condition come about. So first, I will take a LTI system with a transfer function h of s, and I am feeding an input x of s as an input and taking y of s as an output to the system. Now we know y of s is simply x of s into h of s. Now if I go to Fourier domain, when I substitute h is equal to j omega, you get y of omega as h of omega into x of omega. Now we know that if I take the modulus of this and square it, okay, and compute this integral, there is a factor 1 by 2 pi, okay, compute this integral, I am going to get the energy at the output. So then I am going to write it as mod of h of omega whole square into d omega. This is the result I get. Now from this result, I can actually see that, okay, for a system, for a passive system, the energy at the output will always be less than the energy at the input. Whatever energy you are feeding, which is the energy that comes from x of s, has to be the output, the energy at the output should be less than that, okay, less than energy at this. So this I am going to call it Ey, it is the energy at y, equals, if you see, 1 by 2 pi integral minus infinity to plus infinity into h of omega square into mod of x of omega square d omega, okay. Now this result, we can intuitively see that at every value of x of omega, I am multiplying this by mod of x of omega, mod of h of omega the whole square. Now assume that, first let's show that I am feeding a DC input, meaning x of omega exists only for one frequency, okay. X of omega exists only for one frequency. Then this result should be true for any signal, okay. It should be true for, this is a general result, Ey. I'll write that this has to be less than 1 by 2 pi integral minus infinity to plus infinity mod of x of omega the whole square d omega. This is nothing but Ex. So it follows simply that Ey should be at max. If there are no losses, then Ey should be equal to Ex. It should always be less than Ex. The energy of the output should always be less than the energy of the input. Now using that, I am going to just use this result and show that let's assume h of f has some shape. H of omega has some shape for the magnitude response, and I'll assume that my energy x of omega is a narrow band signal, meaning its energy is concentrated in a very narrow band of frequencies. Okay, so first assume that it is between 0 to b, okay, and the energy is entirely concentrated in this small band of frequencies. Now assume that it's a very, very narrow band of frequencies, such that I can assume h of omega is very at DC, at h of omega at DC or h of 0 is nearly constant for that within that small band of frequencies. In that case, this integral reduces to the value of the integral here reduces to integral minus infinity to plus infinity 1 by 2 pi. I'll simply write it as h of 0 the whole square into mod of x of omega the whole square d omega. So this is simply Ex into mod of h of 0 the whole square equals Ey. Now we know this is less than Ex, so this implies h of 0 should be less than or equal to Ex if there is no loss, but this should be always less than 1. So for a passive system, this condition comes from that low frequency. Now similarly, I will now shift the signal frequency. I will now assume that the band is focused on concentrated away from DC. I mean, let's say DC is somewhere here, omega equal to 0. It can be from some frequency omega x to omega x plus b. Okay, and this result should be true for every frequency. Okay, for every band of frequencies, this result should be true. So therefore, for any frequency of interest, if you are going to realize it using a purely passive RC circuits, mod of h of omega the square should always be less than or equal to 1. For a purely passive circuit, this result should be valid. Okay, so now I am going to use this and then try to eliminate the other possible. So I mean we actually derived there are 7 possible transfer function solutions. So we will try to use this condition and try to eliminate the transfer functions which are not feasible. Okay, so first I said the general case transfer function. I've told that, let me just quickly scroll through the transfer function list. I said that we can ignore these two transfer functions are ignored. Now we'll just consider the integrator, the pure integrator. Now we can immediately see that for an integrator the DC gain is infinity. Okay, since the DC gain is infinity, that cannot be realized using passive RC circuits. Okay, so this is already eliminated. Now similarly, option 4, again it has a pole at DC, which means the DC gain is infinity. Okay, so again even this is eliminated. I am eliminating that transfer function as well. We will get it under certain conditions. If I look at the impedance, it might have this response, but as I said, voltage input and voltage output, current input and current output systems will not have this kind of a response. Okay, now we are left with the first 3 possibilities. Okay, I'll discuss the first 3 transfer functions now. Now in the first 3 transfer functions, the simplest low pass filter, since I said h of 0 is 1, it is 1 by 1 plus s by omega b. Now we know that the Bode plot for this is, it starts at 0 dB, or you can say that if I plot it on a linear scale, it starts at, okay, I'll plot on Bode plot. It starts at 0 dB, which is 1, 20 log of 1, and after omega p, it's always lower than 0 dB. In fact, if you see the real plot, the actual plot, it will be 3 dB lower at the omega equal to omega p. It will be always lower than h of 0. Now consider the other transfer function, which is h of s equals s by omega z divided by 1 plus s by omega p. Now in this case, we know that the transfer function is going to be constant when so if you look at this transfer function, I have assumed that h of 0 is 1, so I will ignore that term. This function, again here there is a condition here. the slope s by omega z. So if you see for high frequencies, for very high frequencies, this reduces to s by omega z by s by omega p. I'm actually, for high frequencies, we know j omega by omega p is much greater than 1. Okay, so I can ignore 1 here. Okay, I have just written in terms of s, but what I'm actually writing is s equal to j omega. So I'm writing s here represents j omega because we're only talking about frequency response. So s automatically means j omega. So this result would be equal to omega p by omega z. So I told you again, in any band of frequencies of interest, you cannot have a gain which is greater than 1. So therefore, your omega p has to be less than omega z in this equation, in this system, whatever I've written here, which means the initial slope with which the function is rising, okay, has to be smaller than the slope with which this is going to fall after omega p. Okay, so this, if omega p equals omega z, you will get 0 dB. The steady state value will be 0 dB. Otherwise, it will be less than 0 dB. Okay, it will be minus, depending upon the 20 log of omega p by omega z, it will be less than 0 dB. Okay, so now the third transfer function is h of 0 into 1 plus s by omega z by 1 plus s by omega p. Now in this transfer function, when we try to plot this transfer function, there are, again we said, there are 3 possibilities. When omega p equals omega z, as I said, h of 0 cannot be greater than 1, so I'll assume it is 1 at max. So the maximum possible transfer function is this. Now first we'll assume a case when omega z is or omega p is less than omega z. When omega p is less than omega z, you are going to start from 1, which is 0 dB. Now you should know that the transfer function should always be less than 0 dB. So first you will encounter omega p, and after that it's going to reduce, and when it encounters omega z, again it's going to remain constant. Now the value of this point is actually 20 log of omega p by omega z. And how did I find this value? It is simply at high frequencies this value reduces to s by omega z by s by omega p, and you get omega p by omega z. Okay, so when you take 20 log of that, you get this value. I am not plotting the phase responses. I mean, here the more important thing is amplitude responses here for simple open loop first order systems. Okay, so which is why we are plotting only the magnitude responses. Now from this result, first we will try to plot the other condition when omega z is less than omega p. Then you will first encounter 0 dB line. First you will encounter a 0, then your gain would start increasing, and then when you encounter a pole, the gain will be more than 0 dB at this point. Okay, and the high frequency gain will also be 20 log of omega p by omega z will be greater than 0 dB or greater than 0 dB or nothing but it's greater than 1. So the transfer function here becomes greater than 1, and this is not possible. As I said, in a passive circuit, energy at the output has to be less than the energy at the input. So this will violate that condition, passive RC circuit. So I will discard this possibility. So when you consider a transfer function, which has a pole, a finite pole and a finite zero, then the realizable transfer function should have, I mean, here I have assumed a case when DC gain is 1. Okay, the DC gain in this system is 1, and so this is a realizable system if omega p is less than omega z. Okay, so I'll just quickly take a small example to show that. Anyways, we'll discuss this example later. So assume that you have R and RC. Okay, now in this system we have discussed in the last class how to find poles and zeros. So this is Vi and this is V0. Okay, so the transfer function for this system, the pole is at omega p for this system is at 1 by, so you know by now you are aware of it. Let me write SP, that is better way of writing it. So if I use a negative word, negative number, it makes sense, it's a left half plane pole. It is minus 1 by R by 2 into C, which is minus 2 by RC. Right? How do we find the pole? We just short the input and find the impedance when Z1 plus Z2 is 0, or we short the input and find the point at which this impedance blows up to infinity. That happens when the parallel impedance blows up to infinity, when R by 2 equals minus 1 by SC, and you get this. Okay. I'm sorry, this circuit doesn't have a 0. I'm sorry, I'll just the circuit I had in mind to draw was, we have a capacitor R and an R. This was the circuit. Okay. Now in this circuit, if you find the pole for this circuit, or SP is actually at minus 2 by RC. You can easily show that the value of the pole is at minus 2 by RC. And the 0 for the circuit is when this impedance blows up. Z1 is infinity, Z2 is finite. So that will occur at minus 1 by RC. Now if you see, 0 is at a lower frequency, but pole is actually greater than 0 in this system. Okay, when I say omega p is 2 by RC, omega z is 1 by RC, it is greater. So when I plot this transfer function, what happens is that you are first going to encounter 0 at 1 by RC. So the transfer function is going to go from here, and it's going to raise to 2 by RC, okay, and till 2 by RC. After that it's going to become constant. But you should notice this function, the DC gain is actually half. It's not 1 in this case. The DC gain for this system, how do you find DC? If you can actually derive the transfer function as well, okay, the DC gain for this system is 0. So instead of this graph starting at 0 dB, it starts at minus 6 decibels. Okay, so the maximum gain at high frequencies, the gain is actually omega p by omega c, which is 2, and 20 log of 2 is plus 6 dB. So since you have started with minus 6 dB, by the time it reaches here, and minus 6 plus 6 will be 0 dB. So even though you have 0 greater than the pole, 0 less than the pole, okay, the magnitude of the 0 less than the magnitude of the pole, it is still a realizable transfer function, because you are not violating this condition that mod of h of omega at any given frequency is always less than or equal to 1. You are not violating this condition. Okay, so this is a practically realizable system. So we have spoken about transfer functions, and we took a generalized transfer function which is for a first order system, which is of this form: 1 plus s by omega z by 1 plus s by omega p. Now what did we say is that if I know this transfer function for any system, then I can actually plot the frequency response completely. So you need to know 3 parameters to plot the frequency response. One you need to know is your DC gain. Okay, the other thing is the location of the pole and the 0 for a first order system. So if you know the 3, then you can clearly plot your transfer function. Okay, so you don't have to derive it. All I am saying is by inspection, if you can find all these 3 quantities, then you are done. Now there is mainly one case. Once we talk about realizable transfer functions, there is only one case where this may not be sufficient. The only case is when you have a 0 at 0. So when you have a 0 sz at 0, in that case the transfer function will be something like h of 0 into s by omega z by 1 plus s by omega p. Okay, now in that case, if you see here, there is no, because the DC gain is 0 for a system with 0 at 0, the DC gain is, when you weight s equal to 0, you get 0. So how do we then characterize this? Is you need to know the slope. You need to know the way in which the function is behaving for low frequencies. For low frequencies, this function reduces to h of 0 into s by omega z. Okay, so you need to know that initially how the function is behaving as a function of s, and this again, this term, the initial slope of the function, can be found from circuits using some simple intuitions. Okay, we will take up some circuits and try finding these parameters. Okay, so this is all about frequency response. The transfer functions, I wanted to speak about practicality and how realizable the transfer functions are, and then I'll also talk a little bit about steady state and initial values. So once you have a transfer function, the transfer function has, I'll now start using the word frequency response. H of s, when evaluated at s equal to 0, s equal to j omega, you get the frequency response. Can be written as h of 0 into 1 plus j omega by omega z. Is a generalized first order transfer function, plus 1 plus by 1 plus j omega by omega p. Now if you are given this transfer function, okay, then your aim is to find outputs for step responses. So we'll try to see what will be the behavior of the system for sudden inputs. So now whenever I said impulse, step, these are all sudden inputs. The input changes suddenly. So that is equivalent to applying an infinite frequency. So h of infinity will tell me the behavior of the system when you apply a sudden input to the system, the behavior of the system at t equal to 0, or wherever, when I say t equal to 0, that is the point where your input is being applied. There is a sudden change in the input. At that point, the gain for the system will be equal to h of infinity. So in this system, h of infinity will be simply h of 0 into, if I take j omega by omega z, will be much greater than 1, and this will also be much greater than 1. This term will converge to omega p by omega z. So this will be omega p by omega z. Okay. So for any system, this term h of infinity will be h of 0 into omega p by omega z. Okay. Now h of 0, which is a steady state. So once your input attains steady state, for example a step input at t equal to infinity attains steady state. Okay. So the value your output will take at y of infinity, this is for only true for steady state inputs, will be h of 0. Steady state is like DC. Okay, it's like DC. So h of 0 into x of infinity. Your input is also in the steady state value. That will be your steady state output value. And from this I said that sudden transient, the moment at t equal to 0 you apply a sudden transient, your y of 0 plus, I can say it's actually 0 plus, will be, okay, because it's a causal system, so when the output responds only after you apply the input. So that's why I've written 0 plus. So y of 0 or 0 plus is equal to h of infinity into x of 0. Okay. So the gain for this system, whenever there is a sudden change in the input, okay, will be depending upon the frequency response value at for very high frequencies. So if you know these two values, then you can predict the input and the final values for the system. Okay. So we'll very quickly take a very small, I'll just take a very small example of this circuit, of a circuit to explain what I was describing now. So we'll take a circuit with R1 C1 as a potential divider circuit with two connected with two parallel networks, RC networks, and an input is applied here. Let's say I apply a sudden step 0 to Vx. Now you are monitoring V0 at this point. Okay. Now before we solve this problem, I'll just very quickly discuss that if I have a resistor and a capacitor in parallel, R and C in parallel, we know that at low frequencies, let's try plotting the impedance of the capacitor. 1 by Sc is the capacitor, 1 by Sc is the capacitor impedance. If I substitute j omega, I will get 1 by j omega C. The magnitude of the capacitive impedance on a logarithmic scale will be a linear line like this. At omega equals 0, it's infinity. Okay, it will be a linear line falling off at the rate of 20 decibels per decade. Now for the resistor, it will be 20 log R, it will always be constant. Okay, so there is a point where both of them become equal, and that point will be your pole, which is 1 by RC. So if you look at this network, RC network, and I'm asking you to plot mod of Z of omega, which is your frequency dependent impedance, you will, whenever two resistors are in parallel, the lower the resistance will always dominate the overall, will be the overall resistance. Okay. So now if you see in this part, your capacitive impedance is very high, resistive impedance is very low. So the overall response resistance will be this. It will follow the resistive impedance, and eventually when there is a point when your capacitive impedance 1 by j omega C in terms of the magnitude will become equal to the resistor. So that will occur at omega equal to 1 by RC. At that frequency, the resistive impedance and the capacitive impedance will be same in magnitude. Okay, they will be different in phase, but magnitude they will be same. After that, your capacitive impedance will become very small and it will start dominating. So this will be the Bode plot for the impedance. It's shown in green here. So at 1 by RC, the impedance will be, if the value at DC, the value of this impedance is simply R, because capacitor is an open circuit, you get R. The value at 1 by RC will be R by root 2. Okay. So that will be your impedance of a parallel RC circuit. So for very high frequencies, it will behave like a pure capacitor. For very low frequencies, it will behave like a pure resistor, a parallel RC circuit. In the same way, if I take a series RC circuit and try plotting the impedance of the series RC circuit, now we know whenever two impedances are in series, the larger impedance will always dominate. That will have the dominating effect on the overall impedance. So the impedance of a capacitance, I am plotting this on a logarithmic scale. So we will roll off like this, but omega equal to 0, it will be infinity. Now the impedance of a resistor again is constant. Now here, as I said, previously it was a parallel, now they both are in series. The larger the resistance, that will dominate. Okay, larger the larger impedance will always dominate. Now, so it will asymptotically follow the capacitive impedance at low frequencies, because that is larger at low frequencies, and at high frequencies eventually it will touch the resistive impedance, because capacitive impedance will become very small. They both are in series. Capacitive impedance will become very small and it will behave like a resistor. At 1 by RC, both the magnitudes of the capacitive impedance and the resistor impedance are same. At that frequency, okay, the value will be, I will first discuss the steady state. In the steady state, at infinite frequency, capacitance will be like a short circuit. So the impedance will be purely R itself. So at omega equal to 1 by RC, it will actually be root 2 R. Okay, actually 20 log of root 2 R. I am just showing you the value of this function, the magnitude of this function. Okay, so this is how a series RC impedance will look like. When I plot the series RC impedance as a function of frequency, at low frequencies it is dominated by the capacitor. At high frequencies it is dominated by the resistor shown here. So here it will behave like a capacitor, here it will behave like a resistor. For a parallel RC circuit, it is the opposite. At low frequencies it will behave like a resistor, and at high frequencies it will behave like a capacitor. Now what do you mean by low frequency? For frequency is much less than the pole 1 by RC. Okay, that's your low frequency. High frequencies, for frequency is much greater than 1 by RC. For omega is much greater than 1 by RC, that's your high frequency. Okay, it will behave like a capacitor. Now keeping these 2 points in mind, we will just quickly solve this problem. So you have R and C. So R1, C1, R2 and C2 connected in series, both are in series, and it forms a potential divider network. So whenever you find the transfer function, you need to know, if I want to quickly write the transfer function for this circuit, you just need to know the DC gain, the pole and 0. If you know that, that is sufficient. You don't need to know the high frequency gain. The reason is that once you fix the DC gain, so for example if I draw the plot, once I fix my DC gain, which is h of 0, then if I encounter a 0, first assume I have encountered a pole, then I encounter a 0. Okay, if you know this value, then this value is fixed, because we know how does the system behave after a pole and how does the system behave after a 0. If you know the location of 0, you know the behavior of the system, so you can exactly predict the value of this. Okay, that is why for most first order systems there are 3 unique parameters: the DC gain, the pole, location of the pole, and the location of the 0. If you know these 3, then you can write the transfer function exactly. Now instantly when you look at this circuit, I am going to write the DC gain. DC gain, I can ignore the capacitors. In their 2 parallel circuits, the capacitive impedances won't matter, they are coming in parallel. So the circuit will simply reduce to R1, R2. So the DC gain is R2 by R1 plus R2. Okay. And the next thing is to write the poles. I have already discussed how to write poles for this. The poles in this circuit is simply 1 by R1 parallel R2. You can go back to the previous lectures. I have already discussed how to write the poles for this. Okay, into C1 plus C2. And the 0 for this circuit happens when this impedance blows up, and that will happen at minus 1 by R1 C1. Okay, of course these are all left of plane poles. So if I write minus omega p, I will get minus 1 by RC. Okay, so then the transfer function is pretty simple. The transfer function in this case is just R2 by R1 plus R2 into 1 plus S R1 C1, okay, S by omega Z, which I have written here, and then plus 1 plus S R1 parallel R2 into C1 plus C2. Okay. Now what happens to this circuit at very high frequencies? So at very high frequencies, the circuit reduces to, I can ignore the resistors, so then it will simply reduce to two capacitive network, a network consisting of two capacitors, circuit consisting of two capacitors, C2, C1. The transfer function will be simply C1 by C1 plus C2. And you can very easily show that when this function, when for very high frequencies, I can ignore the 1, this function reduces to S R1 C1 by S into R1 parallel R2 into C1 plus C2. This multiplied by R2 by R1 plus R2. So these terms will cancel out. S and S will cancel out. You will be left with C1 by C1 plus C2. Okay. So that's your transfer function at very high frequencies. As I said, if you know the DC low frequency, DC transfer function and the poles and zeros, high frequency gain is automatically determined. Okay, it can't be a different number. It's dependent on these three parameters: the low frequency gain, pole, and the zero. Okay, that's it. Now, how to find the poles and zeros for how to find the transfer functions for systems with 1 0. If a system has 1 0 at DC, then how do we find that? Let me just, I think I'll do that problem now itself. It's a very small problem. So let's assume we have a circuit like this: capacitor, resistor, and a capacitor, R, C, and C. Now you can instantly show that this system actually has a pole at DC, a 0 at DC. So you applied VI here, V0. How do you show that? You just equate this impedance to infinity. At that frequency, this impedance's value is simply R. Okay, it's in parallel, so impedance is R, so it's finite. So I can apply that condition. You have a 0 at DC, and then the location of the pole, you can ground the input and find the point at which this impedance goes to infinity. That will occur at 1 by 2C into R, R 2RC. Okay, this is a left of plane pole and a 0. Okay, so now to write the transfer function, I know the transfer function is going to look something like this: some constant S plus 1 plus S into 2RC. This is the transfer function. I need to find what is the value of Sk. Okay, now to find that, what I am going to do is, this is nothing but I told you, you need to know how does the function behave at low frequencies. So then we will use basic circuit understanding. At low frequencies, this circuit can be very simply reduced to a capacitor and a resistor, because the other capacitor hasn't come into the picture yet. It's a parallel, R and C are in parallel at very low frequencies, very close to DC. It will behave like resistor itself, the parallel network. So you are reduced to the circuit like this. Now you should know, at very low frequencies, the impedance of this capacitance is actually given by 1 by SC. Okay, and since the capacitive impedance is 1 by SC, in fact, you can write from this itself the transfer function for a system is SRC by 1 plus SRC. So then I can find the slope from this point, or I'll just tell you a slightly different way, more intuitive one. So if I apply an input Vi here, most of the input falls across Vi. So I can assume Vi is entirely falling across that. So the current flowing through that is given by Vi by 1 by SC. So Vi into SC. That current will flow through the resistor. That will be your V0. Okay. So if you see, the slope at low frequency is simply SRC for this circuit. So this circuit is simply SRC by 1 plus 2 SRC. Okay. So that's how I wrote the transfer function. Now there is other way of writing it as well. What you can do is try computing the high frequency gain. At very high frequencies, the circuit will be simply C and C. So the gain is half. Okay. Now at high frequencies, this circuit will reduce to Sk by, this transfer function will reduce to Sk by S into 2RC, and this is equal to half. If I equate the high frequency gain, S and S cancels out, you will get the value of K as RC. You can find it in that way as well. Okay, but this is a very intuitive. Whenever you have a circuit, a capacitor and resistor, the low frequency gain of that circuit will be approximately SRC. And I told you that even in the last class, that this circuit will behave like an differentiator, okay, given by SRC as the time constant for the, SRC as the transfer function for the differentiator. Okay, so in that way you can guess this transfer function. So by that I'll just quickly look at the circuit, draw the low frequency equivalent, write the slope for this function, and I also know the pole, so the transfer function is complete. Okay, so with this we can actually predict the behavior of systems using this simple intuitive techniques. I mean, we'll be able to write the transfer functions. Okay, in the next class I will link the transfer functions to time domain outputs. So we'll actually take several examples. Probably I think I'll maybe spend two classes on analysis of finding transfer functions and solving these problems in time domain as well, and trying to correlate both the frequency and time domains. Okay, so I'll stop at this point.